Thanks for the invite to start with. It is a pleasure to be here. It's my first time in Le Mans. It's all new. It's a surprise. But Thomas and I were colleagues during our time at Ensted. We were doing our PhD around the same time, and we kind of shared the same topic because we were doing plates. So Thomas was more on the experimental side. I was more on the numerical side. And I'm going to show you plates again at the end of this talk, so that thing sort of stuck with me for a long time. But the title is Explicit, exactly energy-conserving methods for Hamiltonian systems. So what I'm going to talk about today is numerical methods. I know that one person in the audience is doing finite differences, at least. I don't know if any other of you is doing any numerical approximations. But that's mostly what I do in my research. I simulate a lot of systems numerically. So for me, it is really important to have numerical schemes that are reliable, that are fast, and that's what I'm going to present today. So the framework is Hamiltonian systems. That's probably something you have encountered in your physics or mathematics courses. So we're going to start by defining the kind of Hamiltonian systems we're going to look at today. So for that, you need a bunch of particles. In this case, we have n of them. So we are assuming that the system is composed of n particles. And they've all got a position in space, which is described by a coordinate q. So q is a vector here, and that includes the coordinates of all the particles. And as you can see, the coordinates only depend on time t. But then to define the Hamiltonian systems, you also need the momenta that are denoted p. Again, this is a vector of n components, and p is also just a function of time. So the Hamiltonian we're looking at has this form. There is a kinetic part called t, and a potential part called v. And you see, we're already kind of making an assumption here on the form of the Hamiltonian, because we're assuming that the kinetic energy is only a function of P, and that the potential energy is only a function of Q. This is not the most general form of the Hamiltonian systems, because you might have Hamiltonian systems where the kinetic part, for example, is also a function of Q, or the potential is also a function of P. So in particular, we're actually even going to make further restriction on the form of the kinetic energy. So we're going to assume that the kinetic energy is just expressed as 1/2 the transpose of the momenta p times the mass matrix, the inverse of the mass matrix actually, times p. And well, we're not making any assumptions on the potential v, but we're going to make assumptions later. So Hamilton's equations are just given as the time derivatives of Q and P, and if you read Hamilton's theory, you just have that the time derivative of Q is equal to the gradient of the Hamiltonian with respect to the momenta, and the time derivative of P is equal to negative gradient of the Hamiltonian with respect to the coordinates Q. But because the Hamiltonian has got this specific form, then the time derivative of Q is just equal to the inverse of the mass matrix times P, and the time derivative of P is equal to negative of the potential, the potential V with respect to Q. Sometimes it is more convenient to lump these two equations into one equation, so you can combine them, and you end up having a second order in time system that sometimes is more convenient to work with. So this is Hamilton or Newton's. So you can switch back and forth between the two systems, and they're equivalent. Okay, you just need to initialize the system. So here we're just assuming that the system is defined for positive time, and you need to give initial conditions on both the coordinates and the momentum. And the most important properties of Hamiltonian systems is that the Hamiltonian is conserved over time. So if you plug in the values of the initial conditions into the Hamiltonian, that value will stay constant. So the time derivative of H is going to be 0 at all times. So like I said at the beginning, we are already making assumptions on these Hamiltonians. So I'm not considering the most general version of Hamiltonian, but I'm only considering Hamiltonians where M is symmetric and positive definite, so that we can actually invert it. And then, like I said, the second assumption we made is that the Hamiltonian is separable. So the kinetic energy only depends on the momenta, and it is a quadratic form of the momenta, and the potential energy is only a function of the generalized coordinates q. But here now I'm making a third assumption that the potential V is non-negative. Okay, so this is a third constraint that I'm imposing on my system, because the systems I'm going to look at all rely on the fact that the potential energy is non-negative. So this is a very important property, because when the potential is non-negative, because the kinetic energy is also clearly non-negative, then you can bound, for example, the norm of the momenta using the value of the Hamiltonian, which is conserved, times the largest eigenvalue of the mass matrix M. Okay, so you can use these numbers in order to bound the value of the norm of the momenta over time. So I have a series of animations now to show you what I mean by that. So like I said, the most important property is that V is positive. So on the top graph, I have a function of, I have a plot of V, and this is just Q. And on the bottom, I have the so-called phase space. So I have Q on the x-axis and P on the y-axis. And the mass is just, can I play this again? I don't know. Well, the mass is just moving up and down because the energy is conserved. So this value over here is the value of the total energy, which is equal to the initial energy. And then your mass will just be moving up and down, and it will form this ellipse in the phase space. So this is the easiest case of a quadratic potential, which is essentially a linear problem. Then you can have different potentials. This is, again, a potential that is non-quadratic, but where the potential goes to infinity for large Q. And again, you have that the motion is bounded in phase space. So here, this dashed line represents the region of the quadratic potential. So you can see here that the mass is sort of going past this region, but still the motion is bounded. And then you can have even weirder potentials where this one, for example, doesn't go to infinity, but the initial energy is sort of lower than the asymptote at infinity. And again, you have bounded motion in both Q and P. Another case where I have the same potential as before, but where the initial energy is larger than the asymptote at infinity. And as you can see now, the mass is not bounded in Q anymore, but it is still bounded in P. So a bound in P always exists when the potential energy is non-negative. So all these cases are good for today's talk because the potential is non-negative. What is not good is a potential like this one, for example. So here, the potential is, we don't know whether it is going to be positive or negative. And you see that motion is going to be unbounded in both Q and P. So there is some kind of instability. And we don't want that. So this is probably the most important slide of today's talk. So I'm just going to spend some time explaining it. The whole point of the numerical method that I'm going to describe later is energy quadratization. So we have this constraint that V is non-negative. That means that somehow you can define an auxiliary function psi, which is defined just as 2V plus epsilon. What is epsilon? Epsilon is just a positive gauge constant that only shifts the 0 point of the potential, but doesn't change the dynamic overall. So it is important numerically, but for the moment, you can think that epsilon is equal to 0. It doesn't really matter at this time. So you can just define psi as being the square root of 2e. And instead of writing your Hamiltonian systems in terms of Q and P alone, you want to write it in terms of Q, P, and psi. So the first thing to do is to just replace the original Hamilton's equations using this newly defined variable. So the equation that changes is the equation that describes the time derivative of P. So you just substitute what you had before using psi, and this is what you get. But then you kind of want to define the time derivative of psi as well, and you can do it very easily using the chain rule. So the time derivative of psi, which only depends on Q, is given by the gradient of psi transpose times Q dot. That's just a chain rule. And I'm going to define this vector G, which is just the gradient of psi with respect to Q. So that's just a notation thing, okay? So now I'm writing an augmented system of three equations. That's sort of an augmented Hamiltonian system, where you have, again, the time derivative of Q, the time derivative of P, and the time derivative of psi. And you can keep switching back and forth between the original Hamiltonian system in two equations and this augmented system in three equations, because in continuous time, these systems are completely equivalent. But what is the important property of this augmented system? If you assume that G is known at all times, then the resulting system in Q, P, and psi is linear. Okay? Meaning that if you're smart in the way you design the numerical algorithm that integrates these equations in time, then you're going to end up with a structure that is linear by definition. And that means that you can do very difficult nonlinear problems using probably very easy techniques that come from linear theory. And that's the reason why we want to work with this augmented system rather than the original Hamiltonian system. So let's move to the numerical methods now. I've got a few more slides with a lot of equations, but then I have a lot of figures later. So bear with me for another 10 slides or so. Some notation again. So here we will have to work with a lot of vectors that are defined for a continuous time t. Now we're looking for numerical approximations of these vectors in time. So the notation is that UN defines the time series at the time step n. So n is an index, a natural number, a positive integer. And the notation UN means that we are evaluating the solution at the time Tn, which is equal to n times k, where k is your sampling period that is also defined as the inverse of the sample rate, okay? So that's just notation. So we're gonna look specifically at three different integrators for Hamiltonian systems. The first one is Sturmer-Verlet, which works directly with the Newtonian form of the system. And the second one is this scheme that I found pretty interesting. It's from a couple of years ago. And this is an explicit, approximately energy-conserving method. I'm going to talk about these methods in a second, so I'm just presenting them here, but I'm going to go into the details of them in a minute. And then there is this explicit, exactly energy-conserving method, which is the one that I'm proposing to use here. So let's look at Sturmer-Verlet first. This is probably the easiest scheme you could think of. So you just integrate, the continuous equation using a very simple approximation of the second time derivative. And then, everything that happens here, well, it doesn't matter because all you're doing is that you are evaluating the gradient at the current time step. So you don't really need to do anything complicated. So Qn plus 1 is your unknown, meaning that Qn and Qn minus 1 are assumed known from previous time steps. And well, there is really nothing complicated here. So this system is super fast because it's fully explicit. There is not even a linear system solve to do, it's just completely explicit. There is another property that is often described in books, which is simplicity. And people make a big fuss about this property a lot of the time, and they never really understood why, because, okay, it's some kind of geometric property in phase space, but this scheme is not energy conserving in general, meaning that simplicity alone, it would not give you a stability condition for the scheme. So you don't really have a conserved positive energy for this scheme. And in fact, the scheme will go unstable, and we'll see examples of that later. So the problem with people that like us work in acoustics is that usually you need to use a very small time step to integrate your equations of motion. That is usually audio rate, so 41.1 kilohertz or something like that. And you're looking at solutions that exist for, I don't know, dozens of seconds. So you are using very many time steps in there. And the problem is that if you're not careful with how you design your numerical scheme, then the solution is going to blow up, and nothing will come out of your computer simulation, and you will have to run it again using an even smaller time if you don't have conditions on stability. So that's why stability is really, really important for us. So this second scheme we're going to look at is a scheme by Marzotto and colleagues from 2019. And this is an explicit, approximately energy conserving method. So this looks more complicated than before because you have basically two equations. This first one, which is again an equation on Qn+1, which is unknown. And then the second one, which is on Pn plus 3 halves. So P is evaluated on an interleaved time grid. But then there is also this complicated, well, maybe not so complicated, but there is a continuous integral over here over the gradient of V. And this integral is continuous, meaning that you need to evaluate that analytically. So this scheme is, again, fully explicit in the end because everything that is on the right-hand side of the first and second equation are assumed known. So again, you don't need to solve complicated linear systems or nonlinear systems. It's fully explicit. But the scheme depends on the computation of this continuous integral. So there are a couple of issues with this. Well, not issues, but a couple of features in this scheme. The first one is that obviously you need to compute the integral in order to advance your scheme, and the integral might not be available in closed form, so you will have to use some kind of approximation in order to compute it. And the second property is that this scheme actually conserves a discrete energy. And as you can see, the discrete energy has a form that resembles very closely the continuous energy we saw at the start. But what is the difference? The difference is that in continuous time, the quadratic form for the kinetic part is positive definite. But here, if you look closely, this vector transpose is computed at the time step n plus 1/2. And the one on the right is n minus 1/2. So it is true that this energy is an approximation to your continuous energy, but the kinetic energy is not positive definite anymore, meaning that despite the energy being conserved, you would not be able to use this form of the energy to prove the stability of your numerical scheme. And that's why I'm proposing to use this scheme instead, where, as I told you before, G, which includes all the nonlinearities in your system, is now evaluated at the time step n, meaning that G is known at all time steps. And the rest of the system, where you integrate Q, P, and psi, is completely linear. Okay? And the good thing about this scheme, I mean, it's hard to see, but just trust me on this, is that there is, again, a form of the discrete energy that is conserved, but compared to the previous scheme, in this case, the energy is positive definite, because the kinetic part is positive definite, and the potential part is just expressed as the square of the auxiliary function psi divided by 2. So this is the sum of two non-negative quantities, and therefore the energy overall is non-negative, meaning that we have the same properties, the same energy properties as the continuous system, exactly as in the animations that I showed you a couple of slides ago. So this is great. The problem is that it is not immediately clear to see that this scheme is also fast. Remember that Sturmer-Verlet and the scheme I showed you before, they are fast because they're fully explicit. But this one on the surface doesn't look so fast because you can use this equation into this equation and then this equation into this equation. And what you end up having is a linear system to solve, which is A times step n times q times step n plus 1 is equal to bn. So A and B are known, meaning that the coefficients in both the matrix A and the vector B are all known. But A is the sum of the identity matrix plus the outer product of a vector alpha and a vector beta. Meaning that A is actually a full matrix, it's not even sparse. So this system looks very complicated and inefficient to do, but this is the trick. This is a perturbation of the identity matrix, and the perturbation has got rank 1. So this, guys, is one of the most important linear algebra tricks you will ever know. So if you're able to cast the system as a rank 1 perturbation of the identity matrix or a diagonal matrix, then there is a very fast inversion formula that always works. And it is due to just Sherman and Morrison. It's a very old paper. It's like 70 years old. But these guys figured that you can do this inversion using order n operations. So you don't need to compute, sparsely linear system solves or full linear system solves. All you do is contracting vectors of length n together. So this inversion is really, really fast. And that's why we can say that the scheme is also explicit, because you don't need to run expensive Gaussian elimination. You don't need to run expensive linear system solves. You can do all these operations very efficiently. Okay, so now we're going into the case studies finally. I have fewer equations and more animations. And the first case study is the simple harmonic oscillator. This is like the best sort of like test bench for anything. Like I always start with this system because it's the simplest one, but you can figure out a lot of stuff just by running your schemes on this test problem. And there are a lot of reasons why you want to use this scheme, this system. Well, first of all, because it is really simple, and second of all, because there is a closed form solution. So you can always check the results of your numerical scheme against the closed form solution. So, well, this is super simple. We only have one particle, and the Hamiltonian in this case is just given by p squared divided by 2n plus m omega naught squared q squared divided by 2. Okay, so you remember I told you that psi is defined up to a gauge constant, epsilon, which is a positive constant. So here I am running a bunch of simulations using different values for epsilon, and I'm also comparing against Sturmer-Verlet. So Sturmer-Verlet is sort of like our reference here, and then we're checking the results of the simulations against Sturmer-Verlet. So this is the time domain simulation. As you can see, well, you have oscillations and everything looks the same. But okay, it's really cool to look at these, but you would not be able to infer a lot of properties just by looking at stuff oscillating on your screen. So what you want to do is to plot the convergence curves instead. And because we have a closed form solution, what I'm computing here is the absolute value of the difference of the numerical scheme at the last time step, minus the analytic solution at the same time step. So I have error curves over here. And I don't know how well you can see because the resolution is not ideal, but a lot of stuff happening. First of all, when the gauge constant is 0, you see that the error curve is sort of like not converging. You would on the x-axis I have the sample rate, and on the y-axis I have the error. So you would think that as you increase the sample rate, your error should decrease. And in fact, when the gauge constant is 0, the error is not decreasing. So even if you look at the time domain simulation, it looks like the scheme is doing something reasonable, but actually this scheme is not converging because the slope is not going down. As you change the value of epsilon, you have a couple of interesting things. So second order accuracy, this loop is 2 for a value of epsilon equal to q naught omega naught squared, which is this curve, and a value of epsilon, which is very large, 100 q naught omega naught squared, which is this. And then Sturmer-Verlet, you see, completely overlaps the error curve for large epsilon, meaning that the proposed scheme is essentially equal to Sturmer-Verlet when epsilon is large. But then I was just playing around with like simulations, and I came up this other value of epsilon, which is 1.39207 q naught omega naught squared. Don't ask me how I got there, okay? A lot of sleepless nights just simulating the harmonic oscillator. But I eventually found this value, which is really good. Like it even seems that you have higher order accuracy somehow, which is weird, but I mean, that's what I'm getting out of simulations. So I don't really know why that's happening. So I'm investigating this particular feature, but all I want to say is that the gauge constant is sort of important.
What is the final time in your previous simulations?
Oh, I think it's like a second.
And what about if you do this for dimensionless units of the order of 10 to the 5? So very long simulation.
Like 10 to the 5 seconds.
No seconds, without units. So when you normalize everything and you run for very, very long time.
Well, I mean, the sample rates here are like really long, I mean, really big. So like a second is probably millions or millions of time steps already, you see? So like if you're simulating a second of output, that means that the scheme has run for millions of time steps. So I think it's a pretty reliable metric of the error in this case.
If you change your final time, then this magic number will be the same, or?
Yeah, it will be. Okay. Cool. So let's move to sort of more complicated problems. And this is a more complicated version of the harmonic oscillator, because here we have a number of masses, and the masses are all interconnected together. They all have a linear spring on the left and a cubic spring on the right, so that the force on the ith mass is equal to omega divided by 2 times qi minus 1 minus qi plus qi plus 1 minus qi to the power of 3. So this is a nonlinear problem where again, you have your Hamiltonian expressed as the sum of the momenta plus the potential, and the potential is non-negative, as you can see. And again, this is a very old problem that was introduced by Fermi-Pasta-Ulam in 1955, but it's been used as test case by a lot of authors. Oh, unfortunately, the resolution is pretty bad over here. So what I hope you can kind of figure out what is going on. But essentially, here I am simulating 6 particles, and I am initializing the fourth particle using this value alpha. And the initial velocities are all 0, okay? So I'm simulating all these systems using a time, sort of like a large time step because it's only 10 to the minus 3. And then computing the solutions against the reference solution, which was obtained using Sturmer-Verlet with a time step of 10 to the minus 6. So again, in the megahertz. The colors are pretty bad, but here, okay, the first plot is a value of alpha that is sort of small. So you see that all the schemes pretty much give you the same solution, and they are all pretty much overlapping the reference solution. And the reason is that there is not a lot of nonlinearity in here because alpha, the initial condition, is small. But then you can increase the nonlinearity by using a larger initial alpha. In this case, it's 50. And as you can see, at the initial times, the schemes are sort of consistent, but then some of them start losing consistency over time. And by the way, here, the sort of light blue line is that approximately energy conserving scheme that I showed you earlier. So I am using that scheme here too. And the other lines are Sturmer-Verlet and the proposed exactly energy conserving scheme. And well, you can increase the value of alpha even further, and then you know, again, you will start seeing errors coming into the simulation at even earlier times. So you see that, you know, after 1.5 seconds, like all solutions are basically away from the reference solution. So again, you can plot errors for these schemes. In this case, we don't have an analytic solution to compare against, but we can use, you know, Sturmer-Verlet with a very short time step and use that as the reference solution and compute error trends according to that reference solution. So you see that all schemes have a slope of 2, which is nice. In this case, I only used epsilon equal to 0 for, you know, the quadratized schemes, but they seem to work in this case, so there is concurrence. But the funny thing is that the shaded areas here represent the values of Sturmer-Verlet and the approximately energy conserving scheme. And in these shaded areas, those schemes are unstable. Whereas for the exactly energy conserving schemes, you can still run simulations and you can still observe this slope of 2. So this energy conservation stuff is really, really important because you see that the schemes that are not energy conserving will give you unstable simulations. Whereas the proposed schemes actually are stable and you can still run them. And this is also a very important plot because it gives you an idea of what energy conservation is when you're using computers. So this is the relative energy error where I'm computing the value of the discrete energy at the current time step. I am subtracting the initial value, and then I'm dividing everything by the initial value again. So this is some kind of you know, relative energy error. And obviously this should be 0 because we said that energy is conserved, but computers do not understand 0, so they understand Martian accuracy. And you see that this graph is of the order of 10 to the minus 15, which is basically, you know, the resolution of your computer in floating point arithmetic.
What is dt here? What is your dt to get this accuracy? Your time step?
Oh, it doesn't matter. You can use any time step and you will always observe errors of that.
The order of 10 to the minus 15.
Yeah.
And what is the system here?
What is the system?
Yeah.
It's the Fermi-Pasta-Ulam. This one.
With which alpha?
I can't remember exactly, but this property scales with all systems. So regardless of the value of alpha, regardless of the value of the time step, you're always going to observe errors of that order for this system.
Even with the dt of the order of 0, 1.
Yeah. Because energy is always going to be conserved. So
I mean, That's actually,
That's why I was asking about it, because I was just something like
There are
that.
lots of this system.
Right. Cool. Right. Let's move now to, I have another 10 minutes, so then we can take questions. We're moving now to cases that are sort of closer to what I do, so musical. In this case, the nonlinear string, which I've worked on for a long time. And this is a continuous system now. So far, we worked with discrete systems, and now we're moving to continuous systems. So the string is now defined over a domain, a continuous domain. And the string is defined by two coupled differential equations. The one in U, which is the vertical displacement of the string, and the one in V, which is the longitudinal displacement. So when you look at nonlinearities in strings, these motions are coupled via this equation. So V now is a potential density that looks sort of weird because you have these quadratic parts that are sort of the linear part of your system, and then this awful square root of stuff, and a minus sign over here too. So it is not immediate to see that this potential is non-negative, but actually it is non-negative. So we are still in the case of applicability for our schemes because this potential is also never negative. And the system is conservative. So if you take the integral of the kinetic energy and the potential energy density, then you would end up having an energy that is conserved and positive. But the question is how you get particles out of a system that is continuous. There are many ways to do that, and essentially you kind of want to semi-discretize your problem in space. And one easy way is to use finite differences, where you define a grid of points on your domain, and you define finite differences. And all of a sudden, from a continuous system, you end up having a bunch of particles, UM and VM, because you're just considering a discretization of them. So if you do that, and then you end up with the same differential equations as before, only that now U and V are vectors that only depend on time because we got rid of space using finite differences. And then you kind of want to define your vector Q, which is going to be the combination where you need to stack up U and V together. And if you do that, you are again working with basically a version of Hamiltonian systems defined for particles. So again, you have a Hamiltonian depending on P and Q, where you have your mass matrix, which is just the identity matrix times some constant, and then your potential V, which is the sum of these potential densities defined at the grid points. So again, we are in we're again working with a Hamiltonian system defined for particles. So again, here I am doing simulations using an initial condition where I have this parameter alpha that sort of describes how large the initial condition is. So again, when alpha is small, so this is time, okay? And this is the domain of the string, and this is the displacement of the string. So you see that time is equal for all plots. So I'm not considering longer times or shorter times for any of the plots. They're all considering the same time span. And you see that when alpha is small, then the system is completely linear. There is nothing going on. The system is just oscillating up and down in the first mode of vibration and nothing happens. You can start increasing alpha, and the interesting thing is that the frequency of vibration increases. That's expected for the nonlinear string, but still you can kind of assume that the motion is taking place entirely in the first mode of vibration, which is the mode we are initializing with. So we are initializing the system in the first mode of vibration, and we are observing the dynamics that results. You can increase alpha even further, and you see that not only you have higher well, faster vibrations, but you also start observing these modal couplings with a lot of like deformations in the shape of the string. And when alpha is even larger, then you have even more of these effects. Again, you can do a sanity check comparing the proposed quadratized scheme against Sturmer-Verlet, and you see that when the time step is small enough, the schemes sort of converge on top of the same solution. And again, you see that if you run the energy test, you have that same order of magnitude in terms of the error of the energy. So energy is conserved machine accuracy. But the good thing is that now this green line represents the compute time in MATLAB for these new, explicit schemes that I have presented. And you see that the compute time is very much the same as Sturmer-Verlet. The black line is the compute time I had until a year ago using the only energy conserving scheme I knew for the linear string, which was a complicated nonlinear solver. So you see, we are hundreds and hundreds of times faster now using these schemes, but we're also energy conserving. Why is energy conservation a good thing? Well, here I have snapshots of the same three schemes, so the colors are the same. So I'm initializing with some Gaussian function or something, and then I'm observing the dynamics, and you see that Sturmer-Verlet blows up because it doesn't conserve energy, whereas the sort of nonlinear energy conserving scheme remains stable, and the proposed energy conserving scheme remains stable, but the compute time for this one is hundreds of times shorter. And okay, this is sort of a different animation where not only I'm computing the nonlinearity of the string, but I'm also computing the nonlinearity of the hammer, like in the piano. The good thing about these proposed schemes is that actually lump all the nonlinearities into the same nonlinear function, and it will still work. So you can put a lot of different heterogeneous nonlinearities into the same scalar function, and you can do simulations of complicated systems where all the nonlinearities are lumped into one scalar function. Well, this is, what I said before, we are about 300 times faster, so we can do real-time simulations of nonlinear strings for pianos now, which is great. Last examples, then I'm done. The von Kármán plate, which is also a system that I worked on a lot during my PhD, and Tomatic too. So this is sort of a good point of contact. Again, well, you have complicated differential equations that define this system, which is completely nonlinear. But one thing I'm going to mention is the form of the energy. Somehow, this is a very nonlinear system, but the energy is made out of quadratic terms alone. So you would think when the energy is a quadratic form, you end up with a linear system, but actually not. Like here, the system is completely nonlinear, but the energy is a quadratic form. So it is not true that if the energy is quadratic, then the system would be linear. Well, again, you use finite differences to, discretize your problem in space, and you end up having again a form of the Hamiltonian, which is the form we want to apply these schemes. Same experiment. We are initializing the first mode of vibration, and we are scaling the initial conditions according to the parameter alpha, and we are observing the resulting dynamics. And as before, when alpha is small, you observe a linear dynamics where the system only vibrates in the first mode of vibration. When alpha is slightly larger, again, you probably have just the first mode composing, well, making up the resulting dynamics, but the vibration is sort of faster. And then when alpha is large, then you have all this nonlinear stuff going on, which is typical of plates. So again, sanity check, you check that the scheme sort of gives you the same result as Sturmer-Verlet when the time step is small, and well, that's what's happening, so that's fantastic. And again, compute times. see, we had like a previous scheme, which is the scheme I had during my PhD. So I remember I was doing these massive plate simulations, and I would have to put the simulation on Friday and then wait for the results on Monday after the weekend, because I had to run like these very expensive simulations on big plates. So if I had these schemes now, then probably that would have helped a lot. But I guess what can you do? So this is great. I mean, again, I have an energy conservation, but very fast simulations. So that's pretty much that. Like essentially, the take-home concept is that now we're able to design schemes that are both fast and stable, and that wasn't possible until a year ago. So thanks very much for your attention.